Okay, I'm going to do another example. I'm going to do number 28 on chapter 4. And this one says, as the Earth rotates, what is the speed of a physics student in Miami, Florida at latitude 26 degrees, and a physics student in Fairbanks, Alaska at a latitude of 65 degrees? Ignore the revolution of the Earth around the Sun. The radius of the Earth is 6,400 kilometers. All right, so we got to draw a picture here. So what we have is here's the Earth. Okay, North Pole, South Pole. Here's the equator. And we have the first physics student is in Miami, and Miami was at a latitude of 26 degrees north. So here's the center of the Earth. Here is the first physics student. And if you draw a line there, what latitude is your angle from the equator to your location, or how far north or south you are of the equator in degrees. So we got one there, and the other one is in Fairbanks, Alaska, and it's at a latitude of 65 degrees north. So up here, so that angle is 65 degrees, is the other student. We know that the radius of the Earth is given to us as 6,400 kilometers. This is the radius of the Earth, and we're assuming the Earth is a perfect sphere. And since it's a perfect sphere, we just have to figure out then what their speed is. Now, you're like, oh, they're all at the same radius. They are at the radius from the center, but they don't have the same radius from the rotation axis. Remember, the Earth is spinning around the North and South Pole. This is the South Pole down here. And so what this physics student is doing is rotating on a circle like this, where this one's rotating up here. So they don't have the same radius. This is the radius in Miami. This is the radius in Fairbanks. So what we have to do is figure out those radii, and then we can use one of our equations over here. We can probably use this one, would be the easiest. V is equal to omega r. Do we know what omega is? Well, let's look up here. Do we know the period of the Earth? Yes, we do. So I'm going to do this one. T is equal to 2 pi over omega. So omega for the Earth is just 2 pi over t. Or omega is equal to, well, we know the period of one rotation of the Earth is just 24 hours. However, we have to convert that to seconds. So what we're going to do is we're going to say, oh, well, 1 hour is equal to 60 minutes, and 60 minutes is equal to 60 seconds. So we have to convert this, and when we convert the rotation speed to omega, grab my calculator here, we get that two times pi divided by 24 divided by 60 divided by 60 is equal to a very small number. So omega is equal to 7.27 times 10 to the minus 5th radians per second. Okay? And omega, remember, is the same for everybody on the Earth. So we got omega. All we have to do is figure out r, and we can figure out what the velocity is. So let's figure out the radius. So for Miami, the radius here, that radius, is going to be the same as if I did what? Well, remember, this is r, this is r2, right? that distance, the radius, because it's a circle. All these r's, those are all the same. So what I got to do is draw a triangle here. So I'm going to draw a triangle for the Miami. So this is for Miami. I have a triangle that looks like this, where this is 6,400 kilometers. I'm going to convert that and make that 6.4 million meters. Okay? And I know that this angle here is 26, but remember that angle is the same as this angle, so this angle is equal to 26 degrees also, because this was our original 26. Those are alternate interior angles. I need to know that side right there. So I'm just going to do a little trick and say, oh, well that's cosine. Cosine of 26 degrees has to be equal to r over 6,400,000. Or r is equal to 6,400,000 times the cosine of 26. And then I can plug that in here and say, oh, v is just equal to 7.272 times 10 to the minus fifth times 6,400,000 times the cosine of 26. I do that, I get the velocity of the student in Miami. So when I do that, I convert, and I get he's going at 418 meters per second. And if you want to convert that then, just to give you a rough thing, to miles per hour, you convert that, that ends up being about 940 miles per hour. So in Miami, you're going pretty fast. In fact, you're going faster than most planes fly. Remember, most commercial planes fly about 500 to 600 miles an hour. So they can't fly as fast as the Earth is rotating at the latitude of Miami. Now let's look at Fairbanks. And the difference there is now here is our triangle. Our triangle looks like this. This is still R, so this is still our 6,400,000 on this side. But now our R is up here, and this angle up here is 65 degrees. So the only thing that changed here is we can do the cosine of 65 is equal to R over 6,400,000. Or R is equal to 6,400,000 times the cosine of 65. We plug that back in because omega is still the same. Doesn't matter where you are on the Earth. So this becomes 7.272 times 10 to the minus 5 times 6,400,000 times the cosine of 65. And when you do that, you get the velocity in Fairbanks is significantly slower. It's 197 meters per second. And if you convert that to miles per hour, you get it's 443 miles per hour. So that if a jet is flying a circle at a latitude of 65 degrees, and it can go 500 to 600 miles per hour, it goes faster than the Earth rotates. So you actually get ahead of the speed of the Earth rotating. So that's what happens. And if you get to the North Pole, if you get close to the North Pole, you can easily walk faster than the Earth rotates because it takes 24 hours to go around once. If the North Pole is here, I can walk in a few seconds, and it takes the Earth 24 hours to do that. So the biggest difference is it's all about the radius, what your radius is to make that difference. That's how you do number 28.